but he's an old timer here. He was here as a postdoc 2004-5. But to give a proper introduction of Bhavtosh, let me ask Arnab to, yeah.
Okay, I don't know if this is proper or not, but Bhavtosh was, he was the first postdoc who really I worked very closely with after I joined TIFR. And this was a very interesting time because I am a traditional semiconductor materials grower. You grow material, if it puts out light, you keep it. If it doesn't put out light, you chuck it in the bin and you change your conditions and you grow again. Now, at that point, we were trying to grow quantum dots. And I had never worried about looking at things like, let's just analyze the heights distribution, see are there universal scaling rules which can be there. So even materials which don't emit light, but something you can actually make very good use out of them. So Bhavtosh analyzed a lot of the, we were growing this, he would suggest what we could grow, parameters to change and see if there are some universal things we could find out. And then after that, we moved into gallium arsenide nitride, I think, where at this point I had another PhD student. And again, there were samples which would be good, samples which would be not so good, samples which would be crappy. But then Bhavtosh said, okay, let's analyze if there is any alloy disorder in this and how does that look like. And again, is there a universal thing that you can see? Can you plot something, in a different way? So on a log scale, it'll all collapse on the same line, etc., etc. So we had a lot of fun doing cool stuff, both with quantum wells, quantum dots, etc. And then Bhavtosh, of course, had done his PhD at IISc on bulk growth, I think.
Not growth, but
growth.
Not growth, but
and then he went over to the KU in Leuven in Belgium, from there to Nijmegen, and eventually found himself at ICER Pune, where he's been for the last 20 years. ICER Kolkata, what am I saying? And he has hosted me there also. And the interesting thing is Bhavtosh is not it's very difficult to pin him down because he's not this typical semiconductor kind of a person. He tries and looks at all kinds of interesting physical systems. And as you can see today, this is, tipping points and which you normally hear in climate change and things like that, and thermodynamic systems and whatnot. So I'm very curious to figure out what's he doing because I know some of the earliest stuff which he has done. When we've gone over to Kolkata, we've had talks about it. Bhavtosh has come over a few times. So, but it's great to have him give a colloquium here formally. Thank you all for coming in spite of being the Diwali holiday period right now. And over to you.
Yeah. Thanks, Arnab, and thank you, everybody. It's a great pleasure to be here, of course. As Arnab said, I was here in 2005, and it was I really had a good time, and I think TIFR had always been very, very welcoming, which I think is something very special about TIFR, especially for both for graduate students and for postdocs. I think that's something which is very special and really cherish that. Anyway, so today I'll talk about something which we've been doing over the past 10 years. It's, as Arnab said, it's not quite my comfort zone. It wasn't. And I've tried to tune it, given Manoj's instructions, more toward the, not non-specialists largely. So the first half, but basically, so we had been looking at these phase transitions of particular kind, and as something which I myself didn't know. And so slowly, as we started learning, then we rediscovered or relearned a lot of things, and which I'll describe. And it turns out that a lot of the techniques which we are using are what are used in a lot of these complex system analysis. It's quite a big thing now. So I thought, let me just take this opportunity to take the dive into this. And I also, at least the first 20 minutes of the talk, I don't know particular systems, so you can please stop me anytime, but then somebody else has to answer for many of these things which I'll be talking about in the first 20 minutes. And then maybe, let's see. All right, so you can please stop me anytime. So yeah, so this work is done by a number of students. I'm sorry, this is when I put the pictures, I realized a slightly testosterone heavy slide, but anyway. So a lot of PhD students who over the past 10 years who've been involved in this specific problem, and some colleagues who've been mostly been working for samples which we've been working with. And yeah, so this work mostly I'll be talking about is from Satyaki and Taposh. And yeah, but all the other people have also contributed to various aspects of the problem, which I'll not be having time to talk about. So of course, so the way we do science is we normally we work with linear response mostly, and you have a lot of these laws which were discovered in the 18th century or earlier, where the response and the perturbation or the control parameter have a smooth relationship of some sort. And yeah, so linear or slightly non-linear, where there's little element of surprise. And that's something which again goes back in some sense to the scientific method itself, because you would say that to establish some kind of cause-effect relationship, you would want, yeah, some kind of a variation which is proportional or which goes or inversely or as proportional of some sort. On the other hand, so there are a lot of systems in real life which actually don't behave like this at all. And basically, you can put some perturbation, you can load it, and at some point, as the cliche goes, or the proverb goes, the last straw would break the camel's back. And so there's this certain tipping point, and that's something which has been, yeah, this is a book which came out 20 years ago, 25 years ago, and it's really caught the imagination. This is something which has been there, and of course, we're living in an age of catastrophes. So there are a lot of tipping points. One is constantly talking about singularities, tipping points, etc., etc. So yeah, so typically you would think of, yeah, very, very generally, you would distinguish a complex system from a simple system in a sense that complex systems have another attribute which is called homeostasis in some sort, where you essentially your body or the Earth's or of the system which is composed of many, many interacting components would hold on to perturbations to a large degree, and suddenly you'll have collapse. And yeah. And there are a lot of tipping points which have been actively studied because this is something which is happening across fields. So you have, so again, as I said, I'm not an expert in any of these. So, but nevertheless, we'll see that the techniques which people use to analyze them are actually some common theme to the techniques which people use to analyze these. So you have in ecology, you have ecosystem collapse, you have evolution, you have extinction of species, then glacial melting, currents stopping. You can have market crashes, asthma, epilepsy, renal failures. Yes, you have this fight or flight response. So there are these sudden abrupt changes which happen as you tune some parameter. And mechanics, of course, there are a lot of examples in physics. Buckling is one example. And in the thermodynamics context, we'll talk about this is what the talk's going to be about. So one example, which again, as I said, I don't know much about at all, is, but this is something which is, of course, has a great emotional value also. This is about reefs, where these coral reefs, many of them seem to sort of go into this bleach state, where you have this coral and algae symbiosis, and somehow the corals suddenly die off. And you have this kind of a tipping point, which is again being something which is being studied quite a bit. And so the point is that, okay, so this is something which is some kind of metaphor. How do you come to the mathematical description of this? And this goes back to, we were talking to catastrophe theory, which was very popular 50 years ago. And by these two gentlemen. So this René Thom has this theorem, which I really don't understand in any precise sense. And this Zeeman was, again, his lieutenant who really went around propagating it. And basically, it's a theory which defines a mathematical language of sudden changes. And you try to classify changes into a specific number of ways in which they can occur. And we'll just discuss a little more about this, of course. And this is, for instance, this kind of a figure is for those who are physicists, is like, for instance, the liquid gas phase diagram or the Ising phase diagram, where you have this liquid to gas transition. And then there's this critical point, and you can have this abrupt transition across this critical point. You can have this abrupt transition where there's a region of phase coexistence, and you can have this abrupt transition, which is the first order transition. We'll discuss more about this. And then Zeeman went around using these kind of catastrophe surfaces to describe almost everything in the world. So for instance, this is this famous or an infamous image where he tried to describe the flight or fright response in dogs. This is taken from Scientific American, where he talks about, for instance, looking at the dog's face, you can characterize fear and rage, and you talk about flight and fight response. So of course, this is rather silly. And so this basically killed, but this kind of analysis, there was a lot of backlash. In particular, there are these articles, couple of articles which really killed it. And because it's oversold some kind of a vulgar scientism, because if you're doing math, then you better be precise. Otherwise, there's no point in doing math, of course, right? Because math anyway is a limited view of the world. So if you're not even precise, you're giving up the precision or giving up on the precision also, then there's no point in doing math anyway. Nevertheless, since past 25 years or so, it has come back in a big way because, of course, it's a sign of the times because you have all these tipping points and changes and crises which are happening on people are certainly aware of these. And this one is, so for instance, here, there were attempts to apply catastrophe theory to biological social problems with far-fetched assumptions and exaggerated claims. And they basically had this very idealized, simplistic model, and then they tried to just use this kind of metaphor to describe everything. On the other hand, now people actually use certain ideas which already existed here to to empirical data. And instead of looking at, for the experts, instead of looking at these global surfaces, you look at local tipping points, which are in more easy to justify from this kind of a normal forms argument, or for condensed matter, people like renormalization group kind of arguments. It's easier to justify those. So the question which, of course, everybody would like to understand is that, are there any warning signs for these, approaching catastrophes? And this early warning signs is a big field across disciplines. Actually, it's a big topic across disciplines. And the basic idea which I want to convey is that there are specific kinds of catastrophes defined in a precise sense, which are critical. And if those are critical, which again I'll try to describe precisely, then you can have early warning signs. No. First order phase transitions are not. So yeah, first order phase transitions are not. So I'll just discuss that. Okay. Yeah. So there.
The difference that it is not a function. What's on the left is.
Yes. Not so much that, but the fact that so the fact that it's basically there's this there's a line of stability which is vanishing suddenly. Not path dependence. Functional form is not important, but basically so there's this stable fixed point and an unstable fixed point, which I'll come to, and so this coming and colliding, and the point of stability is lost. So that's why it's a critical point, huh? Multistable is there. That is not that important. That happens even in first order transitions. I'll describe this in more detail. So we can, of course, this is, I really want to convey this specific idea and how it's different from first order transitions, because these are the kind of transitions which we have established in our lab. So they've been around for a long time. So that's something which I really want to, of course, emphasize. And so these ecosystem tipping points, using this idea which we'll describe, is used. It's actually really extensive. It's something which I have not really looked at and thought about. But when you try to see, then you see that it's really extensive. So it's in ecosystems where you can talk about various kinds of changes, desertification. We talked about this. I just mentioned these reefs, etc., etc. Similarly, you can have these climates, these circulations, Greenland ice, this glacial melting. So this is huge. This last month's issue of the Quantum magazine, for instance, has a nice article on this also. And for instance, in physiology, you have, so you'll see some keywords. So there's something called critical slowing down, which is there. You'll see, so the early warning signs, critical slowing down, of course, I've picked out those keywords for these slides. So you'll see these keywords. And so there's a basic underlying unifying methodology, which is pretty simple. And it's unifying, which all these different works across disciplines use. So I've just taken a very small subset of these. So, okay, so then what's basically the idea? What is the idea of these early warning signs? Okay. So you can think of, for instance, two potential wells. And so you have a bistable situation, and then you have a parameter which is lifting the potential of one of the wells, such that at some point of the parameter, the stressor, the minimum vanishes. It becomes an inflection point. So when this happens, of course, the curvature goes to zero. So the second derivative is going to zero. And the second derivative going to zero is basically what defines the tipping point. So you had a maximum and a minima, and as you're changing this parameter, they are colliding, and the second derivative is going to zero. And at this point, the restoring force, as we'll define it, I'll just, so for instance, the derivative, yeah, so the restoring force goes to zero, we'll just define that. And there is things like critical slowing down, there is large variance. So these are the early warning signs which people see and try to see, yes. Yes. Huh? It's not a first order phase transition because it's a first order phase transition under noiseless conditions. So actual first order, we'll just come to that. No, it's not a first, in the sense it's not a thermodynamic, we'll just talk about it here. It's a critical, but it's a spinodal point, so which happens only in a noise-free situation. So we'll just come to that. So yeah, so we'll come to that. Sure. Right.
Like in the literature,
yeah, meaning it is critical slowing down. So for instance, in the complex systems literature, so they call, so initially people were not very clear about this, but yeah, so they call it critical slowing down. And they call these critical transitions, but these are actually spinodal, because since Shamik is the expert, so it's basically these are critical transitions, they're spinodal transitions. So these are mean field like transitions. And the critical slowing down is, so yeah, that's the surprising thing that, so first order transitions, for instance, typical first order transitions don't have any criticality. So whereas this is a first order transition, which is also critical. So anyway, yeah, so any other questions or comments? So that's something completely different. That's nothing really. Well, let's not get into that. That's completely different.
The typical endpoint of a first order phase transition is a second order phase transition.
No, so that is different. So I will just come to that.
That is not what.
That is not what this is. Okay.
The net potential on that.
So this is a very general picture, of course. To minima. So the point is, we'll just come to this. So okay, it doesn't matter. Let's see, it doesn't matter. So basically what happens typically is that when you have a noisy system, then you never reach this. So you can supercool or supersaturate something, but you'll always either tunnel out in a quantum system or you'll make a escape. So only in a noise-free situation that you actually, so this critical point is actually hidden experimentally. So it turns out, and this is a surprise, well, in hindsight, maybe not, that for certain systems, you actually can observe it experimentally. So that's our main work, actually. So yeah, so this is, I'm just saying what we've just said. So basically, I can think of some parameter which is varying, and you have two states. So you have a double well situation, and at some point, you get the minima disappears, and you have a critical point. And at this point, basically, since the second derivative, the curvature is, if you like, the resilience, because if the restoring force is related to the curvature, if the curvature is going to zero, then the resilience is going to zero. And physicists actually usually use susceptibility, which is inverse of the resilience. Okay. So yeah, so I've just said this. So basically, so you have two kinds of transitions. The first order transition is basically an activated barrier crossing. So you have these double minima, you have coupled minima, the competing minima, but in a first order transition, you have an activated barrier crossing, whereas in a critical transition, you have a rolling down the hill. So you really need to, because that's where, if you reach this point, only then with the second derivative also the curvature would go to zero. So, okay. So for instance, I've just taken this from one influential review written some time back by this person called Martin Scheffer, who's he's quite an influential figure pushing these ideas. So again, so the idea is that so if you reach a certain critical endpoint, you will see certain early warning signs of these catastrophe flags. Yes, you look bothered. Yes.
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 Of the field.
So if you like, it's a free energy, if you like. So free energy is not properly defined because there's a convexity issue. So this is at the level which we are talking right now. We are just saying that this is, if you like, it's some kind of free energy function. Okay. Yeah. So let's in instance, that would be, we can discuss that afterwards. Okay. But it's a free energy, if you like, with qualification. Right.
It was the condition point.
Right.
At some point, this scenario will come.
It's experimentally, it's never sieged. So this is in the van der Waals theory. I'll just come to this. But experimentally, people have never seen this. It was thought not to exist. So there are essentially three, because you're looking at the, sorry. I'll just come to that. This is the whole, so I'll just come to that.
Well, not see any superheating or supercooling above that.
You see, basically the limit of stability.
Exactly.
Is the limit of
So
stability.
that's
Yes. Yes.
Okay.
Yes.
the superheating limit.
Yes.
of the first order.
First order. Yes. Yes. So that's a critical point. So it's something which is very simple, is the superheating limit of the first order time, which is the critical point. And that critical point is what a lot of these climate people and all these people are talking about. And this is related to, because the response of the system, because if the response of the system in a lot of these dynamical systems can be described as basically the response is related to the curvature, the local curvature of the whatever, some potential function. And as the local curvature disappears, then you essentially, the response becomes very slow, because you can imagine if it's something which is sharp, then things would come down quickly. If it's something flat, and if the response depends on the gradient, then it would be slow. And similarly, fluctuations can also become very, very large. So, and there's long memory, slow recovery. So these are essentially three basic signatures, or two signatures, which are experimental signatures of criticality at tipping point in these systems. So also such transitions can show hysteresis. So this is some figure taken from some place where, for instance, they're talking again about the same example, this coral to algae kind of a transition. And you may have, so basically, I just want to say here that it's also possible to have hysteresis, yes.
Okay. Coral and you cool it and you reduce the acidity, it comes back.
No, probably not. So you have to do other things. So, but the point is that the situation where things revive, the parameters, set of parameters where things are reviving may not be quite the same as the set of parameters where things are dying. Maybe you need to nucleate things, of course, but it will not happen at the same typically. So the set of parameters will be different. Okay, and of course, so there's a lot of skepticism about this also, but this doesn't find, anyway. So, okay, so let's come to my work and let's try to describe this. Typically, thermodynamic transitions are either abrupt or critical, if you're looking at equilibrium situations. So like a liquid gas transition at the critical point is critical, but not an abrupt transition. You have first order transitions, which are abrupt transitions, but not critical. You have lasers, which is not really thermodynamic, but that's a different kind of a singularity. Shamik has a book which describes it also. So which is critical, but not abrupt. So critical abrupt transitions, of course, exist at least since the time of van der Waals. And they are called fold catastrophe, saddle node bifurcations, or spinodal. So we'll just use these terms interchangeably. And for instance, in van der Waals' case, we would just draw the isotherms. So it turns out to be multi-valued. And then these isotherms actually end at these two critical points. It's actually there in mean field theory. Van der Waals equation, van der Waals is a mean field theory. And at this point, in this case, the compressibility, the isothermal compressibility will diverge, because again, the derivative of pressure with respect to volume is going to 0. And as we know, then Maxwell realized that this is a problem. Also, there's of course a unstable regime. So, and what he did was he just made this Maxwell construction, where you made sure that you censor out these unstable branches and this critical point. So thermodynamic equilibrium, a thermodynamic first order transition, is just described by this Maxwell construction. So basically, if I look at the free energy picture, this again approximate, then the Maxwell construction basically makes sure that when you're looking at first order transitions, you are always in the global thermodynamic minimum. So you have so first order transition is a competition between two minima, but our thermodynamic system is always in the global minimum. Whereas you can have delay, you can always supersaturate a liquid or a gas, right? You can supercool a liquid, you can superheat a liquid, supercool a liquid, etc. And so you can supersaturate a little bit, but the point is, yeah, and if you supersaturate it, then you will get a hysteresis. So that's something which we see all the time. But the point is, so let me just maybe, the point is that this critical point is not, it's thought that you will not reach it, because as soon as your barrier is some 10 times kBt or something, basically because the attempt frequency is so large, typically it will just come out.
Very low temperature.
Right.
There is something.
Yes.
Magnetic field.
Right.
We have no fluctuation.
Right. So then, yeah, so that is possible. That is possible, yes.
Then you should see this one.
Well, we have to discuss the specifics, of course. So, okay, so I'll just, so the punchline is that you typically see it in systems with long range interactions. Because the point is that this singularity at some point, if you have finite temperature, then it's a question of how close. But, and again, so this becomes a kinetics problem in some sense. So, yeah. But yeah, you're right. That you can supersaturate, the degree to which you can supersaturate depends on the noise in the system. That is correct. But exactly reaching this limit is thought to be not possible. And this was just to say that typically the first order transition is that you have this barrier, which is basically this competition between, as we know, competition between surface and bulk free energies, and you have these critical droplet, which basically forms this first order transition, right?
Any noises?
So this is a question, it's a hard question. So I don't know. So typically one just deals with just simple uncorrelated Gaussian noise with white noise, huh? Yes, so many special kind of noises can do. So that's a very active field of research where different kinds of noise can actually, colored noise can give you, multiplicative noise can give you a extremely interesting phenomenon. But when one is talking about thermodynamic system, then the noise is typically uncorrelated white Gaussian. Yeah, white noise, Gaussian noise, etc. We'll discuss that, huh? So let's discuss that. We'll discuss. Yeah. No, that's nice. All right. So this is what I just. So this is very repetitive also, because I'm just trying to drive one idea down. But I should just come to my work also, of course. So yeah. So this is as I said regarding. We've already said this that this point is the critical point. Yeah. So yeah, again, just to emphasize, meaning it's. Appeal to authority is not nice, except when you want to say that it's not, what they're saying is not quite correct, because it's just generally the wisdom that you'll often find, for instance, in books and reviews that it's, and which is of course true, that spinodal singularity is really only an artifact of an oversimplified theoretical picture and cannot be unambiguously defined. Reason to that is basically the spinodal transitions are, there's reason to doubt. It's a discredited mean field boundary. That's all correct. But there can be physical systems where mean field theories manifest, and that's basically the point. So what they're saying is absolutely correct, of course. And yeah. So because, as I said, finite temperatures would make this point essentially. So there's much more to be said on this, but that's another talk. Okay. So our work basically, yes. Yes.
This happens only in field theory, that's something across.
So mean field theory, in this sense, you can think of as a situation where you throw away all noise. So if there's no noise and you have a system which is sitting, so you need some noise to form these critical nuclei, for instance. So because you need some fluctuations to form these critical nuclei. If there are no fluctuations, then the system just waits and it should not be there. Yes. Yes, that was the point. Yeah. Any other questions or comments? Yes. Okay. So what we have done basically over the past few years is establish this, that such you can actually have such critical points in thermodynamics. These are systems which many of you would be very familiar with. Then also identified what kind of systems would show this and
What you are saying.
Yes.
Activate that critical, that is clear. How do you
Abrupt and
So abrupt is when there's basically when there's an abrupt change in a certain physical property, let us say, things like density. So you have a liquid to gas transition where the density changes suddenly, right? So that's like an abrupt transition. And critical transition is when this change happens without a nucleation. Okay, so or if you, so that's one way to say it, but
not accompanied by abrupt change variables.
So these are two independent things. So critical and abrupt are two independent things. Usually in thermodynamics, critical transitions are not abrupt, and abrupt transitions are not critical. But you can, so this is a situation where you have a transition which is both critical and abrupt. So there are other examples. For instance, even Mustansir has been doing some work, I think, on these long-range systems where you can have critical abrupt transitions, which are quite different from this. But this is one example, and which goes back, as I've said, to van der Waals. And it's kind of physically obvious that in a noise-free situation this would happen because you don't have any fluctuations to form these critical droplets. Okay, so and then we've actually shown that whatever early warning signs which you were talking about, you actually you can measure resistance noise and really see these early warning signs. So basically, we have identified certain systems and established to some degree, as you can in experiments, of course, there's right that you have certain early warning signs, and what kind of systems are these? So there happens in a huge variety of systems. So for instance, it happens in correlated oxides like NdNiO3, vanadium oxides. It happens in spin crossover materials. You'll see one characteristic feature is that regardless of how slowly you change, you sort of affect the transition, there's always a hysteresis back and forth. And these are thermal hysteresis which you're talking about. And this. Yeah. Yes. So you have to establish. So you have to establish that it's critical. So that's the onus is on me to say that, right? So if it is, because the ability to supersaturate, so what Pratap is saying is absolutely correct, that the ability to supersaturate is only there for a first order transition. So this is a necessary condition or a sufficient condition for a first order transition, but this says nothing about criticality. So first order transition, or certain thermodynamic transition should only happen without hysteresis, because when you're having hysteresis, then you're actually falling out of equilibrium. But this is a sufficient condition for a first order transition, as is latent heat. So latent heat and hysteresis are two sufficient conditions for a first order transition. So then you have things like spin crossover materials, charge density wave compounds, just the whole list of things which people have studied. I'm sure many people in the room also know these. Indian groups have also been very active. So you have manganites, magnetic materials, you have intermetallics, martensites, you have halide perovskites. We've done some recent work in halide perovskites, which actually are these optical materials which also have this. Then you have actually goes back to the 60s when C.N.R. Rao actually did some very nice work. K.J. Rao and C.N.R. Rao. K.J. Rao also used to be a professor at ISC. So they did very nice work, 60 years back. So this is, so the main key message is that it's basically the strain. So all these transitions which I have shown, and this is a subtle point, which they're all basically there's an underlying structural transition and an underlying strain in the structural transition causes long-range fields. And the thermodynamics of long-range systems is very different than thermodynamics. So Shamik is, of course, again, an expert from thermodynamics, the usual thermodynamics. And somehow this long range seems to suppress fluctuations quite a lot. And so these are typically, you think of phase transitions to be diffusion controlled. So these are not diffusion controlled at all. And they're not, in some sense, stochastic. And the barrier, for instance, scales the system size. And then you get these hysteresis loops, and then even ensemble equivalence. There was a lot of work 20 years ago. So this equivalence of a canonical and grand canonical also, with the canonical and microcanonical breaks down. So for instance, even in astrophysics context, actually these are things which people have discovered over and over again. So in astrophysics context, Lyndon Bell in the 1960s, late 60s, actually did some work. And then in the 2000s, actually 2010, people did this, a lot of work. But I think there are a lot of open questions still. People have moved to long-range quantum systems now. But there are a lot of open questions still. And thermodynamics, I think, is still really not settled. Anyway, so, okay. So what we want to show, so what I'll just spend the next few minutes to show is actually our work, where we want to sort of show that, so is the transition critical? And basically, is it really ending in a saddle nodes for these kind of transitions? And so these are rather peculiar, so I'll maybe not spend time on this right now. So as I said, so the phase does not nucleate if the temperature is held fixed. Then you can create a large number of states depending on pathways. You can create hysteresis loops, which people know. Then you can create, so basically temperature just acts like a parameter and it doesn't cause any diffusion. And you can hierarchically ordered states. So let me just skip this. So you can do a lot of things, but let's come back to this. So the question is that given you have transitions like this, are these really saddle nodes or spinodal points? So how do you establish this, right? Because this is something which, of course, people have seen. So the idea is, again, so a naive way to look at this would be that as you're going, say, on the top curve, the free energy picture is going like this. And at some point D, basically, this minimum is disappearing somewhat. And the first derivative, of course, is always 0 at the minimum. The second derivative also goes to 0, and the barrier against nucleation is vanishing. And similarly, if you go back, so this is like a metal and insulator, two states with, again, you get two critical points, which I'm calling the spinodals, where the barrier against the nucleation would vanish, resilience would go to 0, or equivalently, susceptibility would diverge. So again, we just go back. So this is just to remind you that these are the catastrophe flags or signatures of spinodal criticality or saddle node criticality, which one would like to see, or any criticality. And so for instance, this is just somewhat of a simplistic view of what we've been doing. So you just have, say, for instance, you have a resistance, and you can think of resistance as depicting the order parameter. And then what you're doing is that when you're looking at resistance noise, so what you do is you just measure the resistance very precisely and throw away the signal and just look at the noises, something which many, many people do. In India also, there are many groups who are doing fantastic work here in this context. So you just measure the resistance time series, the noise. And as you're changing one of the parameters, you just sit at a given temperature and measure the time series. You change the temperature again, measure time series. And the point is the nature of the time series would change as you approach the spinodal or the critical point. Okay. And so this is just, this is the only math slide which is there somewhat. So yeah, so this, as I said, so the restoring force is like, the derivative of the free energy with respect to some order parameter, and there's some little noise. And I can just Taylor expand around this minimum. And so the second derivative is basically like the resilience, which we've been talking about, or the inverse of the susceptibility. So as the resilience goes to 0, the susceptibility would diverge. So if I can just linearize this equation, this is just a linearized version of this equation. So I'll see that as this goes to 0, basically the relaxation times would diverge, fluctuations would. So this is, And so this is the math, the simplified math which we have done here is basically the same math which you also get for second order critical transitions. It's just that the nature of critical point is very, very different. And yes, please. It doesn't matter. So the point is that it doesn't really matter because, so that's an interesting question because because you see things which are actually temperature, it doesn't really matter in this window. It's really not mattering. So we've looked at certain characteristics. It really doesn't seem to matter. So temperature is really like a parameter. Okay. And then specifically one would like to measure, for instance, this, so the signatures would be, you would like to measure phase ordering times, and you would like to look at the autocorrelation, the response of the function, and you would like to look at the variance. So these are the three signatures which one would like to look at. So which is what we were saying here. So these are the three signatures basically which you would like to look at, and you can precisely under certain, not precisely, under certain approximations, at least you can try to measure these. And so for instance, you can measure the phase ordering time. So you just go close to the particular temperature to how best you can given experiments. And then you try to fit certain time scales, and you see that indeed at the two ends of the resistance curve, you see that there's a growth in the relaxation times, which is the phase ordering time. And then one can also measure the noise. And so noise, basically, as I said, you just sit at a given temperature and try to measure fluctuations carefully. And you're just looking at this, which we just discussed. And for instance, the autocorrelation relaxation time also is diverging here. And so these are two systems, VU2O3 and Indian IO3. Both these, you can see that these correlation times diverge is too strong. Experimentally, you see a clear, unambiguous growth of these. Similarly, you can look at this variance, which is in some sense an analog of critical opalescence. So again, see, and it happens on a log scale. So it's happening on both the cooling as well as the heating spinodals. And yeah. Which one? Sorry, so okay, so I should have mentioned this. So yeah, so basically you have this time series which you measure. So you just measure this time series, so basically keep the temperature fixed and you measure time series very, very carefully over, or carefully, not very, very carefully, let's say, over a few hours. And then you basically look at, you do various kind of maths on it. So you can look at the correlations, autocorrelation of the time series, you can look at the variance of the time series and things like that.
So parts of that time series,
how
they correlate with each other.
Yes. So that will tell you, for instance, so if there's a random kick at some point, so how long the memory of that random kick is remaining at a later point. So that's typically the autocorrelation function, which is, so okay, I have not plotted it here, sorry. But that is what, so you can fit some function, you can get some characteristic time approximately, and using some prescription. And this prescription is not unique, but the qualitative behavior will be the same. Okay. And sure, yes, take it for what it is. Yes, that's true. That's true. That's true. So yes, it's not, so yes, this is actually, so, so this is something which is very interesting, and maybe if I have another 5 minutes, so let me finish, and then I have some slides which actually we're still doing some work, and maybe I'll come to that, okay? So that's basically the point is, so if you like, one way to look at it is that, of course, you have finite noise, right? And you're measuring something with noise. So, but this is a very important question. So the point is that in some sense, you can think of these long-range systems as being qualitatively different from short-range systems. And so you see this property, but an effect of finite temperature sort of broadens the transition. The broadening is in some way similar to, for instance, what happens in a finite size effect. So you can actually treat this broadening exactly at par, at least experimentally, that's what we've tried to do, as a finite size effect, just as so any finite temperature broadening. So there's a finite temperature broadening, because of course there is a finite temperature broadening, but you're able to come close enough to the spinodal or the critical point that the singularity is not completely masked and it does manifest. Okay. So that's something which is very important. So for instance, one thing which one can try to do, which is something which we have tried to do, as Pratap was also mentioning, that you can look at supersaturation as a function of temperature. And so you're controlling the noise. And then you can see how the supersaturation is changing with temperature. I'll just maybe show that. I have some slide. Maybe I'll just show that quickly, but that's an important point. Okay. But yeah.
This gas price exchange. He's studying very much down in the if I see on the dashed line, you have one point that has come down a lot, which is very close to the.
Sure, yeah. So
why do such fluctuation?
Because see, these are hard measurements, because what you're doing is actually looking at a time series. So this is actually, each data point is data over few hours, right? and you're actually looking at the statistical features of this time series. So you look, yeah, but you're looking at the noise signal. This is not the real signal. This is a noise. So this is a noise signal. So whatever. So this is a noise signal, and you're looking at the time series of the noise. And the thing is that this is, and so for instance, this other system is a little better, but that is true. And you see this combined with other signatures. So there are other signatures which you see, for instance, you see relaxation time divergence. And then you also see, so again, so these are not very, very strong signatures. But yeah, and you also see these things. These are also not very, very strong signatures, but they all come together. And you see them both exactly at the heating spinodal and the cooling spinodal. And for both systems. So it's just that there are a lot of things which are coming together, but that's true. So this is what it is for experiments. And yeah, so basically, I have some more stuff. So if you want, we can discuss. But basically, I just wanted to close here. So yeah, so the whole point was to basically we looked at this in these physical systems. You have this math of the catastrophe, which is really manifesting. And yeah, and that's okay. Yeah, so this just shows that, so this is basically some parameter. So let's say some theoretical parameter. And so this so basically you have a certain surface. So this parameter is the fixed points of a certain solution. So you have these fixed points. So you have a stable fixed, unstable fixed point and a stable fixed point. So you maybe say in this case, so you may not always have a potential picture. So, but you can have solutions to equations, or in this case, even in this case of here, you have this a stable fixed point and an unstable fixed point, right? And so you're looking at solutions. So solutions are given by the fixed points, or the minima or the the extrema of this. And so you're just drawing the locus of these extrema as a function of a certain parameter which you're changing. So in this case, it's supposed to show that our control parameter is changing with time, actually. So this is, or rather, so changing one control parameter with time, and you're looking at the response, so you're looking at the noise in the system. It's actually a slightly dense slide, I should have explained.
Some sort of...
No, it's an analytical form. It's an analytical form. So if this is the analytical solution, then the response of the system would flicker, would sort of show this. And the noise would grow. So this is basically, you're saying that this is noise, which is, so this noise has certain characteristic. This characteristic is, for instance, this correlation, this AR1, or the auto-regression features is actually, it has a long memory. There's more variance. There's things like that. So this is just showing the response of the system. And this is what would happen if you have a set of stable equilibrium solutions. And at this point, the stable and the unstable solutions are coming together and colliding in this saddle node. Okay. Yes. 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 So insulating. So yeah, actually, for instance, here, right.
An artifact coming in the fluctuation signal from the absolute value of the resistance of the sample.
Yes. So this is again, so
like the magnitude of your fluctuation, because it will be like you're passing some current, and so the voltage delta V will be I times delta R, right? And if the variation, the overall R is large, does it also affect your the fluctuation signal?
So, well, these are details which one needs to look at, and one has, of course, looked at those things. But what I was saying was, so one thing which I just firstly want to mention is that you always have this 1/f noise signal. And so that, in some sense, sets the flow. Yeah. And you get something which is over and above that. Okay. And I don't have figures for absolute values of the noise. So, but you typically can divide it by R. Okay.
Yeah, that's what I'm asking. So if you have different values of R that you are...
So at each point, you can divide by R. So you can get the noise and you can divide by R. And you see a local increase in that. Yes, but that's, yeah.
So because, and second question was, I mean, have you seen this criticality manifest in some other physical property? Like, I mean, some acoustic wave, or I mean, something which is not resistance.
So no.
The resistance will also have the background from Johnson's law.
More than that, just 1 by F. Just 1 by F. Johnson is much lower. 1 by F is always there. Yes. Yes.
In VATIO3, you have the soft phonon modes.
Right.
Right. And that's like the inflection point of your.
Right.
So a soft phonon mode is similar to a critical point, right?
Exactly. The same thing. So for instance, if you're looking at, so this dynamical equation which I've written, right? So this dynamical equation, it's somewhere there, no? Maybe. So this dynamical equation had so you just had a first, it's a fully dissipative dynamics which one has written. So, but in general, you could also have a second derivative, right? So for instance, when you're doing physics of inflation, you have that for phonons also. Why not for charge density waves, you may have a second derivative also. So when you're looking at high frequency phenomena, so soft phonons, so typically soft phonons should actually, so actually that reminds me, so that's true. So soft phonons, typically again, you see it at the critical point, but there is actually some previous work where people have seen soft phonons in hysteretic systems. And but they didn't sort of have the language or whatever. I shouldn't say the language or whatever. This exists for a very long time. But then they were just called critical points. But when you're saying soft phonon softening in a hysteretic system, that means that you're actually looking at this critical point. So, but phonon softening is basically the same phenomena when you also have an inertial term in the system, this dynamics, effective dynamics. Yes.
My question is about, you say that I reach temperature and then suddenly there is a change. The question is about how fast does this change happen? Are there studies about how fast does this system?
Yes. So in fact, so there are parallel studies over the past few years where people have also seen this kind of critical slowing down, very, very similar phenomena in ultra-fast systems, meaning through ultra-fast probes.
Yeah.
So
how fast?
So people have seen, for instance, in picosecond response. Sorry.
What are the time scales typically?
So people have seen in picosecond response also. And again, in very similar systems. So they, of course, you perturb the system and look at close to the phase transition, you perturb the system and look at the picosecond response. So that shows up in the picosecond response also. There are actually many papers in the past 4 or 5 years where people have actually seen this in picosecond response also. So it seems to, but this is a bit surprising that it should sort of manifest. I mean, theoretically, of course, the time scale should diverge, but that you should see such slow dynamics is actually surprising. Yes. So picosecond is more, it's more digestible, definitely. But these systems do show very, very slow dynamics, and this is what attracted me to them.
Just taking upon the question about, there are other situations where you have these abrupt transitions.
Right.
For example, shocks.
Yes.
You're driving the system, becomes nonlinear.
Right.
And suddenly there's a density jump.
Right.
Or a very small layer.
Right.
Does any of these things apply there also?
Yeah, I think so. I think it depends on, so basically the whole point about a lot of this is that the kind of singularities which appear seem to be limited. So you have only a certain set of singularities, if you're just concentrating on regions around the singularity. So that's actually not too many. And so of course I don't understand, I don't know anything about shockwave physics.
Easier to do things there than.
Sure. In the sense one can, one has.
Can also give you signals in the optical region.
Yes.
In whatever region you can think of.
So right now, for instance, one of the
emission from those, the shock region. And shocks are so universal now.
Right.
You have the whole universe beaming out this signal.
This is very fascinating, but I actually don't know anything about the nature of the singularities of shock waves. But I think that's actually very, very fascinating. Of course, these shock waves are, and one more thing, of course, which I didn't discuss at all, is to look at spatially resolved dynamics. So more recently, we've been doing microscopy and light scattering and try to actually study spatially resolved dynamics, because then you can get some K-resolved modes also. So that's one of the things which we are doing, yes.
It's just because you mentioned about the buckling phenomena.
Right.
So typically in a buckling, Euler buckling, that's
Right,
the
right,
incident that you're talking about. In the Euler buckling phenomena, if you try to tap it slightly, and do an oscillatory force on it, you can see the soft thing coming up, right? In your systems, you're measuring a DC current, you're measuring a DC response. Would an AC response give you something different?
So AC would be, so what the time scales are, right? So, the assumption, the belief, or whatever you like to call it, is that on the time scales which you're probing, these are dissipative systems. So, and you're looking doing some hydrodynamics because, looking at some effective order parameters is also not very well defined because actually the native order parameter for this system, nobody knows, in fact, what the native order parameter for these systems are. It's so complicated. So you just fudge an order parameter, say the insulating phase fraction, and then you define, so it's something which is very, very approximate. So, but the time scales to actually perturb a system electronically or even phonon modes, you have to go to gigahertz at least.
No, okay. So the simpler question would be that if I look at the AC susceptibility, would that have any indications of this fluctuations?
So I think you have to, again, I don't know, I think you have to go to at least, meaning the capacitive effects have to operate. So you have to either affect a phase separation. So in the sense, you do see certain peaks in percolation, for instance. So which is a slightly different, again, this is a complicated question. We should discuss this. But typically you would imagine that this AC, the innate AC frequency for these systems would be at least gigahertz. And the description which we have is completely hydrodynamic of a dissipative system.
Kilohertz, standard, then the phase factor is not changed.
I'm saying that yes, so it's basically equivalent to DC. It's equivalent to DC, basically.
Any other questions?
Yes. So if you want, I can show that for those who are interested, this thing about the effect of noise. Yes.
So, see, you have some divergence in the resistivity noise, which could be a signature of the critical fluctuation, but the divergence is not very large.
Yes.
Now, if one wants to really eliminate any other possibility, do you have any system where you have the hysteresis, but you do not see the divergence? To just eliminate that not something else is at play here. It's a regular first order transition where you don't have the divergence. Do you have any such example, or have you come across any such example?
No. So the thing is, so then what one has to plan an experiment as to, so what happens is that typically, so there are various things. So for instance, the way these experiments are done is that actually these systems are completely, maybe I have something here. So they actually over hours, nothing really happens. And if you're measuring time series. So first order system would typically nucleate. So you can supersaturate it a little bit, but typically they would nucleate.
Yeah.
So in fact, even quantifying the nature of noise is very, very difficult in a system.
No, I understand. But what I am saying is that unless one understands the simple situation completely, it's difficult to rely on data on more complicated system. For example, when high TC was discovered, a lot of very exotic phenomena were found in high TC almost every week. And some of them are actually exotic. Some of them transpired to be not exotic at all. You could get them in conventional superconductors also. Only thing, no one had measured it. Later, when people measured it, you can find it there as well. What I'm asking is that one has to eliminate the effect on the simple system before one can really conclude this as a signature of critical fluctuation in a complicated system.
So one more signature which I have, okay, can I just quickly show that, is also, since I think it's formally we are close, so I can just show that. So for instance, here, maybe I have it somewhere. So for instance, you can also do this dynamic hysteresis study. So it doesn't work for all systems. And you can just do this quench rate dependence and you see how the transition shifts. So it's an independent study. And if you have a mean field like system, then there are very specific predictions for the exponent. And it should really be 2/3, for instance. And you actually see, but you don't see this in all systems. The first time when we did this, many years ago, you actually see an exponent of 2 by 3, and this is what is actually theoretically predicted. If you just do a simulation for a noise-free situation. So there are, so this is very, very important, and one has to be, but this is something which is an independent thing, but it doesn't always happen. This happened in V203, and this was just very, very clear. Many, many times one did it and very carefully. Yes, so.
Classical one, but I don't see any of these divergences.
No, but also you tell what, it would be very nice, you tell what other experiment you can think of. Yes. Sorry.
The direction at what Pratap was asking.
Yes.
So if you are saying that from the measurement you claim that there is a divergence and you try to relate to this scenario, wouldn't there be like any other critical transition? You have scaling relations. You make different quantities and find relations. From just this phenomenological theory, you will be able to construct those relations.
Yes. So, okay. So
do you have such evidences?
Yes. So this is of course, so what we have tried to do, which again we're just doing. So this is actually another, so this is, I'm doing with this very bright student, Kalimuddin from, he's again, TIFR's grad student. Mintu was a PhD student here. So this is looking at, this is a very similar experiment. I got into this because they were doing very, very similar experiments, where again, they're looking at this charge density wave transition, which also has a similar saddle node kind of a singularity. So this is unpublished work, which we are just working on right now. So you have a similar saddle node and you see this divergence. And then, for instance, what you can do is you can do this at different temperatures. And then you can basically, so I don't need to tell you this, but you just, for instance, for finite size singular scaling, so you can actually see so there's more details to this. You can try to do a finite size scaling analysis, for instance. So as I said, it's like noise broadening the transition. In a way, in the same sense as you would have a finite length scale. In the sense, if you have a finite system, you can think of it doing the same way. In fact, even magnetic field would do the same thing in some sense. So what I can try to do is I can try to do a data collapse. I didn't write this, but basically you can, do a usual finite size scaling kind of analysis. Instead of L tending to infinity, you take, T tending to 0, and then you try to do a data collapse for whatever it's worth. Okay. So you can try to do something like this. Okay. So yeah. But it is very hard because it's a finite system, meaning because it's noisy, so you always get broadened divergences. So it's very hard actually.
Any other questions, comments? I have a question, but I'll ask you.
Maybe we can.
Let's. No, I think we need to move on to the tea and snacks. So thank you, Bartosz. Thank you very much, and thank you for putting in effort to make it accessible to.
No, it's absolute pleasure. Absolute pleasure.
I really enjoyed it.
Thanks so much.
Thank you very much.
Absolute pleasure. Thanks. Thank you. Thanks.
I was just wondering. My question was, well, let's walk.
Yeah.
We can get this.
I just should get this out.
You have your laptop here.
I just put it.